So today, I want to do this project right here. Okay. So it's this penciled one up here, has a little triangular shape. Okay. And this is the one that we're going to make. And so the short story is that, and this is not algebraically extremely challenging, but I think algebraically it's extremely revealing for the kids, is that if you take a length of steel rod and you bend it into a shape that looks like this, if 100% of the steel is made into that shape, then you know you have an equation, right? And you can just go ahead and call this P because it's going to be the perimeter. And then you can say, all right, well, what do I have? I have X. Maybe I have half X. Maybe I have an S for the length of this side. I have some kind of R. Okay? Can you write an equation that would represent this in general? Okay? And the thing is that depending on how you write your equation, it's going to be short and fat or tall and skinny, or there's many possible combinations, right? And that's the cool thing about it, is every kid makes a steel shape that looks different. And then this length is 91.3 because the raw material that we have is this copper-coated filler rod for gas welding. And this stuff is cheap. This is like $8 for this little bundle. And it's a nice, hardy piece of metal. And when you give a kid something like this and a pair of pliers and a torch, like, you have their attention. You know? And you're going to say, all right, so what you're going to do is you are going to imagine that you are a vending machine. And this is going to be fed into a manufacturing process. And I have a big video. I show tons of manufacturing process videos. Like, this is how the thing makes the shopping cart. This is how it makes nails. Because manufacturing is a place where a lot of rate, process, algebra gets used, like showing YouTube videos of how things are made all the time. So imagine having just seen those. This goes into a machine. At a certain distance, it gets a certain bend. At another distance, it gets another bend. At another distance, it gets a radius. At another distance, it gets another bend, until eventually a finished product that looks like that comes out. Okay, so for us, what's that going to mean? Well, do you see on this assignment down here, it has this 0, 6, et cetera, et cetera, et cetera. Basically, starting at one point, can you mark on here where all of the bends are going to be, okay, as if a machine were going to do it. And then it says you want to solder it on a straight section. Because every kid wants to start right here, but it's really hard to solder this at a corner, and it's much easier to start it right here. So then you have to say, okay, well, I'm actually going to start my solder right here. So that means my first bend is actually going to be a certain distance, so in the end, this is the final product. So the kid will come up to me and say, all right, I'm ready, Mr. Weinberg, check it out. And they'll have all their marks, and I'll say, oh, that looks good. Give them the pliers, they'll twist it into the shape, and then I'll show you how to solder it once you get it built. Basically, because it's copper-coated, you can solder it. If it was all steel, you couldn't solder. So otherwise, you'd have to weld. We don't have that capacity. Just wrap the joint with copper wire, and then pull them from the torch and solder it. So that's the project. You could make it so it looks like this. I mean, depending on the variables you choose, it could be any shape, right? And some of them won't work, right? You can't have your R be bigger than your sides, or there are constraints here, and we're not going to go there right now. The radius of this cannot be greater than, because it just wouldn't work, right? It wouldn't look like that shape. And if R has to be less than or equal to H, don't you have an equation, an inequality? So if for this one, there's actually a system of linear inequalities, because you're saying, okay, my perimeter is, X plus H plus R plus 2R plus R plus H plus another X or whatever. But also, it's constrained by the fact that R has to be less than H. So then you get some graph that looks like this. Basically what I do is I've worked them up. I've done this with pipe cleaners. And, we've just spent a lot of time getting them to the point that they're ready to tackle this. And honestly, I just give them this sheet and I say, go. So this is my assignment to you guys. I'm just giving you this sheet. And I'd like you guys to do this individually. every single person. So I am going to stop talking. And with this piece of paper, I'm going to let you guys roll with it. And when you have your steel and it's all marked, come talk to me and we'll go solder it up.
Well, that's what I was saying, with the angles, right?
Let's talk about these shapes. Can I borrow yours here?
Yes.
Any just reflections on this experience overall? Any comments? Things that were learned, processes, pitfalls. This is pi r, and people are very tempted to call the bottom 4r. Yeah. So this is pretty much the classic, little oversight that people make. Yeah. I'll draw a picture of yours. That was good. I liked it. It was like this. I think that's wonderful because it's a great example of how it's like from taking the concrete and then adding the abstract, and when the concrete and the abstract match, then like you can just tell visually that it worked. And who was the person who made theirs a different shape? Like, oh yeah, so you had yours so that you had a 3S and then S. So like yours came up and it looked different. It was clearly like this. And this was obviously not the same, and it was intentional. Like you decided to change the mathematical relationship, which in turn affected the shape. And so that really, all of these like variations and mistakes are just ways to teach in more depth the fact that there is a mathematical relationship, and that maybe it would be good to get the math, right. So, and if not, you get immediate feedback, and the kids are like, "Oh, check it out! It actually didn't work," And so, a kid can do this, and say, "Oh, well, that didn't work right. I wonder why." And you see them puzzling, and then you figure it out, and they're excited that they can finally make their shape rather than just throwing in the towel because it wasn't right. And so you see the connection, like, oh, I see what's left is got this, and I have to divide that by 4. But that really is the algebraic process, So, and then with the connection I try to make with these guys is like when they, in computer animation, Toy Story, like the ball as it's coming towards you. Well, that is a computer program that is describing the perimeter of that ball as a mathematical function. And the way they make it appear to be coming towards you is they increase the value of the variable on the screen, and it just looks like it's coming at you, but actually it's just a mathematical equation that's making the shape bigger. And so, there are a lot of things. You can put Word documents up and say, look, if you grab the corner of the shape, it scales it up and down, which means it is just changing the value of the variables, just like the shape that you guys just made. So if you make a shape, you can make a complex shape in like Word or whatever, and then you can make the box bigger and smaller, and all of a sudden kids are like, oh, I see, they're just increasing the R, and then everything else is following, or they're increasing the P. So I do this one more time again, and I have them make a shape, write the equation, and then I say, you don't know what I'm going to assign to your perimeter, and so then I give them all very different lengths. But this time I give them like 90 feet of string, and it has the big circle, and they're looking around like 90 feet, like how big is that going to be? And they have to do the math to really figure out like, oh, it's going to be like 18 feet across, and then they're looking for a place to do it. And then I give them a big old handful of little stakes, and they all go outside, and then they have to stake it out in the grass. And then to draw the circle, they have to pin in all kinds of stakes and get a string and draw the radius, And so the project I tell them is, you are going to be marking out the area of a concrete patio that's going to be poured between a set of buildings with a big old fountain, and you need to physically lay it out, and it has to be right, including, and for us on graph paper it's really easy to do it, but anytime you lay something out, out in the real world, what's to keep you from making it a parallelogram? You can't really tell by looking at it, so then they have to do the old 3, 4, 5 triangle trick, and which is used commonly for builders. And so I have all these kids, they make it and the perimeter works, but it totally is like this. I'm like, all right, that's not going to work. What are you going to have to do to guarantee that this angles are right and everything is right? They're like, oh, that's right. So then I need them to show me, like I stand there and they like physically take the tape measure and they prove to me that the angles are right by using the 3, 4, 5 triangle, or they'll put the tape on the 3 or the 4 or whatever, you know. So there's a lot of like application, and kids like this, you know, they get to go outside. So, and almost every school has a field of some type, you know, which is a big old thing of string and a huge thing of chopsticks from cash and carry. You can do a lot. And if it's outside, I mean, you relinquish a little control. You've got 30 kids outside, you know, like with string, scratching their head, measuring stuff, putting stakes in the ground. But it's fun. Okay, so now, mathematically, where do we go from here? R, and you wrote an additional equation that 4R equals S. So you said 4R, 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 R, 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 R. So now what does the perimeter equal? Well, what did we just turn this into if it is all in terms of one variable? What do you call that? We have created a mathematical function. Okay, so now we're going to express the perimeter as a function of R with this relationship, which ends up being something like, you know, who knows what, 18.14 R. Like, oh, check it out. So now what we're doing is we're actually introducing, well before Algebra 2, the whole concept of a function. Because I think, personally, functions are where the power of math really starts. Because it allows you to express big things with a single variable. And if you're expressing things as functions, and you write variables in terms of each other, then you can scale things up and down. You can put them in columns in a spreadsheet, and it will calculate all of the new values for you. And also, if you start with the concept of a function early, it doesn't take that long. Oops, I'm just going to go ahead. So let me just kind of project mathematically where this goes. We just did this for perimeter, which is a linear function. But what about area? And what about volume? So now what you can do is you can start to relate as functions the surface area, the perimeter, and the volume of these shapes. Oh, and check it out. Intersections, systems of equations. What we just did was we created through functions, and we could do it for our shape, a graph the area versus the perimeter of the equation for this shape. It kind of gets to, whoops, x, you know, whatever, 4x, but it gets early on to graphically understanding this relationship.